As an example of the general considerations discussed in the last section, let's have a look at how genetic information could interact with experience to achieve an effective combination of behaviors in a specific domain. And I use the familiar domain of behaviors that name different categories of visual objects. And as we discussed a number of times before, at high level, learning the meanings of words depends on simultaneous activity of auditory and visual columns in the cortex, and this is obviously one way in which a teacher guides learning, by saying the appropriate word when the corresponding object is present. Also, genetic information can specify the existence of cortical areas with receptive fields at the appropriate levels of complexity. Receptive fields able to discriminate between different types of visual objects, able to discriminate between different words, and receptive fields that correspond with groups of receptive fields in those visual and auditory areas that are often active at the same time. So the inputs to those areas and the rough neuron thresholds can be specified in advance by genetic information. So let's have a look at how genetic information and appropriate external guidance can interact to develop category naming behaviors, and I use this conceptual architecture. In the architecture there are visual cortical areas, and they have receptive fields in different areas able to discriminate between different types of visual situations. There are auditory areas able to discriminate between sounds, between sequences, sounds, and so forth. Then there are various polymodal areas we'll be discussing, including an area that develops receptive fields that correlate with groups of columns in another area that are often active at the same time. An area that detects receptive fields correlating with the degree of overlap between two populations of active receptive fields in some other area, say the area that discriminates between different types of visual objects. And two populations in this visual objects area, let's call them P1 and P2 of active columns, could be detecting receptive fields in response to a directly perceived object and to an indirect activation. The activity overlap area gets lots of inputs from this visual objects area, but different columns in that activity overlap area have different biases on the patterns of inputs. The effect of these biases is that if lots of active columns in population P1 are the same as the active columns in population P2, but at some different phase of modulation, some set of receptive fields will be detected in the activity overlap area. But if very few columns are part of both populations, the set of receptive fields detected in the activity overlap area will tend to be different. So the pattern of receptive field detection in the activity overlap area will be different depending on whether the overlap between the P1 population and the P2 population is large or small. There will also be areas that detect receptive fields able to discriminate between complex situations. And these areas are defined genetically in the sense that genetic information specifies their rough size, the areas from which they tend to get most of their inputs, biases on the distribution of inputs across different columns, thresholds for receptive field detections, and the areas to which they tend to direct their outputs. Then, because of these genetically defined starting points, the receptive fields they define through experience will tend to be effective for specific behavioral purposes. The components in the basal ganglia we'll consider include components corresponding with attention behaviors, where by attention I mean processing of receptive field detections in other areas, such as discriminates sounds area, in a manner I'll get into in a moment. Then there are genetically programmed components that drive the muscle movements needed to produce the human phonemes. And again, there's only a limited number of these phonemes across all human languages, and they appear to be genetically programmed. They can all be heard in babies babbling. Before 6 months, all babies babble sounds much the same, regardless of the language spoken at home, because all the phonemes are being spoken. But any the baby doesn't hear gradually disappear from the babble. Then there are genetically programmed components that implement the speaking of sequences of phonemes by driving sequences of phoneme components. The phoneme sequences are selected more or less at random initially. Then there are reward components, and these reward components target other behavioral components to change recommendation weights. So within this architecture, let's have a look at how genetic specification and experience interact. And we'll start in the next section with genetic guidance of visual receptive fields.